Good afternoon, dear friends. At the last lecture, we received a system of equations that describes the currents and voltages in the sinusoidal mode of the line with distributed parameters. Today, we will solve this system. According to the plan of this lecture, we will firstly obtain the solution of the system regarding the voltage in the line. Then the solution for the current will be obtained. In the process of solving, we will introduce so-called secondary line parameters. We will analyze these secondary parameters and consider their physical meaning. But we, as always, will begin this lecture by recalling the summary of the previous lecture. So, in the previous lecture, we obtained a system of line equations with distributed parameters for the case of a sinusoidal signal. To obtain this system, we use images of sinusoidal currents and voltages in the form of complex numbers. We note that the complexes of instantaneous values of current and voltages consist of two parts. The first part is the amplitude value complex, which depends only on the spatial coordinate. But the second one is the rotation factor, which depends only on time. This allowed us to move from a system of partial differential equations to the corresponding system in total derivatives. Mathematics allows us to get the solution of the system in total derivatives. Obtaining such a solution for the line with distributed parameters will be the topic of this lecture. So, in the last lecture, we have got a system of differential equations that relates the complexes of current and voltages at any point of the line with distributed parameters. In order to solve this system with respect to the voltage complex, it's necessary to differentiate the first equation of the system with respect to the spatial coordinate x. As we can see, the derivative of the current is included in the equation that we have received. But we already know the current derivative from the second equation. Substituting this derivative from the second equation, we finally obtain a second-order differential equation with respect to the voltage complex at any point of the line. The equation that we have obtained is a well-known linear homogeneous differential equations of the second order. We have already solved such equations when we studied the topic transient processes in electrical circuits. The equations we were solving were equations for time. Now we have an equation for the spatial coordinate x, but the general method for solving such equations had not changed. As is known from mathematics, the solution of linear non-homogeneous equations of the second order can be obtained as the sum of two components. Each component is an unknown constant of integration, which is multiplied by the exponential function of the x-coordinate. The exponents are the lambda 1 and lambda 2 numbers, which are the roots of the characteristic equation. The characteristic equations can be easily obtained from the corresponding differential equation. To do this, the derivatives should be replaced by lambda with the appropriate exponent. And the coefficients of the characteristical equations coincide with the coefficient of corresponding differential equation. In our case, we obtain such a characteristic equation. It has two solutions, plus and minus the square root of the product of z0 and y0. Let's denote this square root by the letter gamma. Then we get the solution for the line voltage complex, which is shown here. This solution includes two constants that are not known yet. These are two integration constants, A1 and A2. So we have a system of differential equations for current and voltage in the line, this system, and we know its solution for voltage. It remains for us to find an expression for the current in the line. To do this, we express the current from the first equation of the system, as shown here, and substitute the derivative of the voltage which is already known. After simple transformations, we get expressions for the current at any point on the line, which is shown here. Note that the expression for current also included the same integration constant A1 and A2 that we included in the expression for voltage. We can find these constants later from the boundary conditions. In the meantime, let's introduce the concept of secondary parameters of the line. Firstly, let's pay attention to the exponent of the exponential function, which is included in the expressions for current and voltage. We denote this exponent by the letter gamma. We said that gamma is equal to the square root of the product of z0 and y0. From the last lecture, we already know what is z0 and y0. You can see the corresponding slide of the last lecture here. Both of these numbers are expressed in terms of primary parameters of the line and the angular frequency of the sinusoidal signal. Thus, we can express the gamma coefficient in terms of the primary parameters of the line and the angular frequency of the sinusoid. This factor is called the propagation constant or propagation factor and is the first of two secondary line parameters. It is a complex number and shows how the current and voltages change as they propagate along the line. The real part of this complex number is denoted as alpha. It is called the attenuation factor because it shows how the amplitude of the current and voltage decrease as it propagates from the beginning of the line to its end. The imaginary part of the propagation factor is called the phase coefficient or phase factor. It shows how the initial phase of sinusoidal current and voltage change as it propagates along the line. Now let's talk about the fraction gamma divided by Z0. This fraction, as we see, is present in the equation for the current in the line, in this equation. Consider the inverse relationship, Z0 divided by the gamma, or divided by the propagation factor. Substituting the values of Z0 and gamma for, as shown here, after simple transformations, we get this expression. Under the square root in this fraction, the numerator of which is measured in ohms and the denominator is measured in Siemens. If ohms are divided by Siemens, we get ohms squared. Extracting the square root, we see that the fraction Z0 divided by gamma is measured in ohms. That is, it is impedance. This impedance is called the wave impedance of the line and is another one secondary line parameter. The physical meaning of the wave impedance, which is designated as ZW or Z wave, we will learn later. Thus, in addition to the four primary parameters, the line with distributed parameters is characterized by two more secondary parameters. These parameters are propagation factor and the wave impedance. The propagation factor and the wave impedance are called secondary parameters because they depend on the angular frequency of the sinusoidal signal in the line among the four primary parameters. Given the introduced wave impedance, we can write the equations for the complexes of voltage and current in the line as shown here on the slide. As we have already said, we can find the constants of integration that are present in these equations using the boundary conditions. Our lecture has come to an end. Let's summarize. So, it's some conclusions of our lecture. Firstly, The system of line equations with distributed parameters for the sinusoidal mode makes it possible to form a differential equation with respect to line voltage. This differential equation is a well-known linear homogeneous differential equation. His solution is not so difficult. The solution of the equation for the line voltage is the sum of two components which are unknown integration constants. The propagation of voltage along the line is determined by a secondary parameter called as propagation factor. The propagation factor is a complex number. Its real part shows the attenuation of voltage or currents, and the imaginary part shows how its initial phase changes. There is one more secondary parameter in the equation for line currents. It's called as wave impedance. The integration constants that enter into the equations for voltage and current can be determined based on the boundary conditions. The definitions of these constants will be a subject of our next lecture. Thank you very much.